Good day to all of you. So, today in this session, we shall discuss and learn about the state space representation. So, today's title would be state space representation. So, in the previous class, we discussed about the basics of modeling and how we represent any system which may or may not be a nonlinear system in a small signal manner, such that the small signal model is a linear model. So, today we will extend those principles and try to apply them on simple circuits to get a generic approach or generic method of obtaining a state space representation of a physical system. And then using these general concepts, we will apply it to the DC-DC converter circuits and see how we can get the state space representation of DC-DC converter circuits. DC-DC converter circuits being slightly different from the normal continuous power physical systems, in the sense that they are switched power. You have switches apart from just R, L and C's, and these switches make the power flow to be having a switching pattern, and these need to be addressed when we are trying to model the dynamic model of the DC-DC converter. So, when we talk of state space modeling, we need to understand what a state is and what it represents. Therefore, we start from the energy concepts. So, if you have a power source, and we have a power sink. So, normally this power sink is what is known as the load. We are familiar with that term, and the energy or the power starts flowing from the power source to the power sinks in this manner. So, when power starts flowing from the source to the sink or source to the load, this could be a battery, it could be a DC power supply, and the load could be a resistance or any other equipment connected to this. There are four possible actions or events that can happen. One possible event that can happen is dissipation. So, specific to the electric domain, dissipation implies this event happens through the component called the resistor. So, some of the power which is flowing from the power source encounters resistors, and some of the power is lost within the resistor and gets converted to heat. Another thing that could happen is storage. The power can get stored in the stored as energy in some components, and the storage can be in two ways. One is called the kinetic storage, kinetic energy storage, and another type of storage is called the potential energy storage. energy storage. So, the kinetic energy storage happens with a component called L, or the inductor in the electrical domain. You have equivalent components in other domains like the inertia in the case of the mechanical domain. So, here the energy is stored by virtue of the movement of the charges, or by virtue of the flow of the current, and the energy is given by half L I square, where I is the current flowing through the inductor. So, if you have an inductor L and a current flowing through it, and that inductor is supposed to have an energy built up within it equal to half L I square. Likewise, you can have another type of storage called the potential storage, energy storage, wherein this is accomplished by a component called a capacitor. With which is denoted by the symbol C. And if there is a voltage V across the capacitor, the energy that is stored in the capacitor is given by half C V square. So, now all these things are known. Just trying to recap that these are the two mediums through which the energy will be stored, either kinetic or potential. So, apart from these three events, there is one more possible event that can happen, and that is a transformation. The transformation can be in scale. For example, you could have voltage at one level here. The voltage will be transformed into another level at this point by means of a transformer, or you could have an electrical domain energy getting transformed into magnetic domain energy here. So, like this, there could be energy form transfer, or there could be one of the power variables, either potential or kinetic variable, getting scaled accordingly through this transform in a lossless way. So, in an energy transform case, there is neither loss nor storage happening, it's just pure transform. This is what we want to indicate, that in a typical power flow or energy flow from source to sink, these four possibilities can occur, which is dissipation, kinetic storage, potential energy storage, and or transformation of energy or a variable. Now, with this possibility, we have in a clear cut manner three important components. One, as I was saying, is the inductor with L as the symbol. Now, this inductor is governed by two possible governing equations. That is, you could have the voltage across the inductor. So, we have the symbol for the inductor, which is like this. Now, there is a voltage across the inductor, and we shall call it as V L, and there is current through the inductor, and we shall call that one as I L. So, the voltage across the inductor and the current through the inductor are related by this differential equation relationship. V L is equal to L d I L by d t, or you could say I L is given by 1 by L integral of V L d t. So, these are the two possible governing equations for the inductor. Of course, one may say these two equations are the same except that they have been rearranged. However, there is one significant difference, and that is of causality. In the equation 1, the cause or the independent variable is I L, the effect is V L. The current through the inductor is the cause and the voltage across the inductor is the effect. In the second relationship, the voltage across the inductor is the cause and the current through the inductor is the output or the effect in the relation with respect to the relationship 2. And it should be noted that in nature always seems to prefer the causality wherein the integrator is associated, or the integral causality. So, this is the relationship that nature seems to prefer in almost all physical systems, and this is the relationship which we will most of the time be using for developing the models. Okay. This is the integral causal. What it basically means is that that causality which leads to an integral relationship. Likewise, in the case of the capacitor with symbol C, wherein potential storage occurs, potential energy storage, and it is given as half C V square. The capacitor is symbolically represented in this manner. You can have a voltage across the capacitance, and we will call it as V C, and a current through the capacitance, we will call it as I C for this capacitance C. The governing equations for the capacitance also can be put into forms where you have the voltage as the effect output, which is equal to 1 by C integral of the current through the capacitance dt. And you could have the other way, which is the current through the capacitance as the effect and the cause being the voltage. So, C dVc by dt. So, here too you have two possibilities with the two different cause and effect. So, you could have current as the cause, voltage is the effect, voltage is the cause, current as the effect. And here again nature prefers that causality which leads to an integral effect or an integration of the variables, because nature everything is a continuum, everything is continuous. So, this is the one which we will be using for all the models without loss of generality. The third component that we saw was the dissipator, which is called the resistor in the electrical domain, has a symbol R, and it is denoted in this manner. And let us say it has a voltage across that. This resistance R has a voltage V R across it, and the current through it is denoted I R. and it also has two governing relationship VR, which is equal to IR into R. This is the first relationship, wherein the current is the cause, VR, the voltage across the resistance, is the effect. And in the second relationship, IR, which is the effect, is result of VR by R, where VR is the cause. Now, here, as there is no integral or an integral relationship in either of 1 or 2, there is no preferred causality as such. That particular causality which is applicable for a given case is taken at that point of time. So, either this or this can be used in obtaining a model of the physical system. These are the 3 major components which are used in almost all the circuits, electric circuits, and we will see how they get incorporated into the models, and how we get the state space model in a systematic manner. Okay. Now, let us take up the case of obtaining the state space representation by means of an example. Okay. But first, let us see what is it that we ultimately want. So, the state space representation is given in this fashion: x dot, which is equal to A x plus B u, and y, which is equal to C x plus D u. All physical systems, all linear physical systems can be brought into this state space representation. This is also called the state. Let me write it down here. This first equation is called the state equation. The second equation is called the output equation. So, this is the standard form which is used for representing all linear physical systems. Now, here you see different variables. You see the variables x, you see the variable a, b, y, c and d. Okay. X is called the x dot is nothing but the derivative of x, d x by dt is x dot. A is called the state matrix or the system state matrix. It holds the property of the system, character of the system, all the characteristic properties get into this matrix A. B is called the input matrix or the parameters, gains related to scaling the input variables. Y is called the output variable, that is the controlled variable, or in general the variable that is presented out of the system. This is obtained from the state variable and a scaling matrix C called the output matrix, directly from the input and a scaling matrix D called the feed forward matrix. Okay. Now, this is the final state equation representation form, but let us see how we go about getting that one. Before that, let us have a block diagram view of this state equation itself, such that we get a better understanding of the inner workings of the system. So, we started with x dot is equal to a x plus b u, y is equal to c x plus d u. So, this we said was the state space representation. What does it imply? So, let us say we have a block. The central block in all the physical systems is the integrator. Integrator is something which is so very much evident in almost all physical systems. Its modeling and the way the nature behaves. It is the central block even in modeling. The output of the integrator contains history, memory. It remembers. The output of the integrator has a memory effect. It can remember its past history, and we call that one as x. So, all the state variables should have should be the output of integrators or should be output of memory blocks. Only those qualify to be state variables. So, that is very, very crucial. Remember that a state variable has memory. It remembers its past evolution or immediate past history. And by virtue of integrator being a memory element or memory block, its output will directly qualify for being called a state variable. So, if x is the output of the integrator, the input to the integrator is definitely the derivative of its output, which is x dot. So, let us see what happens. Every system has a local internal feedback. So, the state x is scaled through some parameters, and you obtain a x, and this is added, summed up with the input, and you have the input u which flows in. It gets scaled by the gains, the input scaling, and we call that one as the B matrix. B represents the input scaling, and it goes to the summer block, which adds up with the output of the integrator scaled value and results in x dot, which is the derivative value of the state, which gets integrated and finally becomes the state vector. Now, this is still not complete. This in fact here represents the state equation portion of the state space representation. Now, continuing further, the output x gets scaled by other parameters. Let us say c will give you Cx, and to that you sum up, add the input which comes directly as feed forward term and gets summed up at this point to give you the output y. So, if you see, this portion is called your output equation or the output equation portion of your state space representation. So, if you look at this block diagram, we see that the input u gets scaled by the scaling matrix B, set of gains, parameters of the system. Then it gets added up with a feedback portion A x, becomes the derivative. This derivative goes through an integrator, always an integrator, becomes the state variable, which eventually is used for feeding back. The state variable gets scaled by the matrix or the gain value C, you get Cx. To this is added the direct feed forward portion of the input scaled by D, summed with Cx, you get the output y. So, every system can be represented in this form. You have an input portion, as shown here. You have the input portion, which is indicated here in the equation. You have an output portion directly from the states, state output, some combination of the state is indicated here. You have a portion of the input, let me call that one as the feed forward, meaning it is the input is directly bypassed and sent directly to the output after suitable scaling. The system is actually avoided and it is taking the bypass and goes through a scaling D matrix, dx, du, and then comes out at the output there. So, this du is actually represented here at this portion of the output equation, and then you have this portion, that is the integral portion plus the feedback portion, the state which is fed back through a scaling matrix and back again to the input of the integrator. Now, this portion actually gives the dynamics of the system, and this is characteristic which gives you the character of the system, and therefore, we have what is called as the characteristic matrix or the dynamic matrix indicating the dynamics of the system is represented by this Ax portion of the equation. So, these two provided Ax and Bu provide what is called as the scope for the next evolution of the variable. So, x dot is actually giving you a prediction, an estimate. It predicts the slope. It says this is the derivative, and the next value of x depends on this particular slope. It will evolve based on this particular prediction of the slope. Okay, that is the derivative, which actually is used by the integrator to achieve the or obtain the next value of the state or the next continuum value of the state. So, this is the format in which every system will be reduced to and appropriately put into these forms: the input portion, the output portion, the dynamic portion, the feed forward portion. In many cases, you may not find all the portions. In many cases, you may not find the feed forward portion at all. So, which means D will be 0, implying that this portion is not existing. And in the state equation also this portion would be absent. So, in many of the state equations where there is no feed forward portion, you will just have this portion, this part of the representation where the output equation is just reduced to y is equal to Cx. This is also very, very common. So, our job now is to bring any system, whether electrical or otherwise, into this format, and the DC-DC converters are also to be brought into this format. So, now let us take up a very simple example, which all of you would be familiar with. So, let us say we have an input source, a resistor, and a capacitance, this form. You have an R and you have a C. So, the system actually is made up of this. This is our plant under consideration or system under consideration. We have an input, we will call it as Vg, and we have an output, we call it as V naught, and there is a current flowing through this particular circuit into the through the R and the capacitance. Now, let us say we want to represent this particular circuit in the state space form. How do we go about doing it? So, step 1, we identify the energy storing elements. So, the number of energy storing elements directly give you is a direct measure, direct indicator of the number of integrals or integrators that you will have in your model, because as we saw in a few moments ago, that you have 3 possible events apart from the transformation, which is dissipation, kinetic energy storage, and potential energy storage. So, the kinetic energy storage and potential energy storage are linked directly to the inductor and capacitor elements in those respective domains, and the inductor, the governing equation is the current through the inductor, which is given as 1 by L integral of voltage across the inductor into dt, and the voltage across the capacitance is an integral which is given as 1 by C integral of the current through the capacitance into dt. So, these two are the integral relationship which is preferred by nature, and these integrals occur only in energy storing elements, as energy is a continuous parameter. So, identify the number of energy storing elements. The number of the energy storing elements is also called the order of the system. The order of the system is is directly connected with the number of energy storing elements in the system. So, in the above circuit, as we see, we have only one dynamic component, one component which is capable of storing energy, and therefore, we have the order of the system equals 1. So, it is a first order system. As we see, just only one energy storing element. Now, next step what you need to do is to identify, step 2, identify the variables that will be used for modeling. Now, this is an important stage which will lead, which will eventually lead you to correct modeling. So, at this point, it is it may be appropriate to mention that any system's response is dependent on 1, the input given to the system, and also dependent on the integrator outputs. Integrator output values. Remember that the integrator has memory. Even if you switch off the system, the integrator outputs will store the previous history, the previous value, and the next state of the value, the state of the system is decided by not only the input, but also the values that are associated with the output of the memory devices or the integrators in this specific case. So, it is good to use these items, the input and the integrator output, as the variables. Okay. The integrator outputs are called, as we saw, state variables. The integrator outputs are called the state variables x, and the input we have been denoting it as u in our state variable representation. Therefore, we need to identify what is u and what is x. All the u's and all the x's we need to identify and list down, and they form the variables that will be used for the modeling. So, if you look at the circuit that we have taken up, which is comprising of a source called V g and two components R and C, and V naught. Now, we know that if we are having C, we would like to use the dynamic relationship V c, which is equal to 1 by C integral of I c dt, the integral equation. So, apparently we see the voltage across the capacitance, the output of the integrator. So, this will directly qualify as being one of the state variables. So, as this is a first order equation, as this is a first order system, there will be only one equation that is sufficient to represent the whole system. So, you have x, the number of state variables is just one, because there is only one energy storing element, will be V c, and then u will be V g. The input in this case is V g, which is also called the control input for this case. So, considering these two variables, you have just these two variables. The whole system has to be represented with just these two variables, plus the parameters, the fixed or the constant parameters that define the system, in this case R and C. These are the only variables that you need to use, and that you should use only these two. Now, let us look at the system based on these two variables only. Okay. Now, start always with the dynamic equations. So, now we come to step 3. So, step 3 is starting with dynamic element, obtain differential equation. This is the third step. Starting with dynamic elements, obtain differential equations if it is many energy storing elements in the circuit. Here it is only one energy storing element, therefore, we are starting with the dynamic element, obtain one differential equation. So, the number of differential equations, will be equal to order of the system. Or the number of energy storing elements, or number of memory elements, if it is the case, or if the energy is very less. So, therefore, in this specific case, we have one energy storing element, therefore, the order of the system is 1, therefore, you will have only one differential equation. So, let us try to formulate the equations for this particular system. in terms of variables Vg and V naught in terms of the variables Vg and Vc. Vc is the voltage across the capacitance. Notice that Vc is equal to V naught, but we will come to that come to this aspect later when we are developing the state equation completely. Then there are two parameters R and C. So, we need to use only these. So, starting with the dynamic element where we have the voltage Vc equals 1 by C integral of I C dt. I C is actually the current which is flowing through the capacitance. The current through the capacitance, I cannot use the symbol IC, the variable IC, because I have to restrict myself to variables in this group set. This is U, the input variable, this is X. These two will go into the A matrix, which represents the system character. Now, this has to get replaced with that symbol set. So, what is IC? Looking at the circuit, we have IC is nothing but the current flowing through R minus the current that would have flown if there was I naught. But right now, this is the open circuit. Now, let us say you are connecting it to a load, an external load, which is R naught. Okay. Then I naught is nothing but V naught by R naught. So, let us replace this IC with this symbol set here, which is nothing but IR minus I naught, which is nothing but Vg minus Vc by R minus I naught, which is nothing but V naught by R naught, but which is actually Vc by R naught. So, you see that in this equivalent value of IC, all the variables have been taken from this symbol set. Of course, R naught is one more item that we have component we have added, it becomes a component element R naught here. So, all the variables taken from this variable list are being used, and it can be written as, this equation can now be written as dVc by dt, differentiating on both sides. I have 1 by C R Vg minus Vc minus 1 by C R naught into Vc. This would form a representation of this equation all in variables which are actually taken from this list. Next step is segregate. Step 4, segregate into form x dot is equal to A x plus B u. All the input states and the input, this is input and states. So, from this equation take all the portions which are corresponding to the states, that is this portion into one portion and the inputs into the other portion. So, x dot is equal to A x plus B u can be written as x dot is nothing but x is a state in this case is Vc dot, that is the first portion of the equation, that is this. Then we are going to take the portions corresponding to the state variable 1 by R c and R naught c, 1 by R c minus 1 by R naught c, both these together are multiplied by the state, and then we take the coefficients corresponding to the input variable V g in this case plus 1 by R c V g. Now, this forms your state equation. This forms your state equation portion of the state variable representation. What is your output? Output should be of the form y which is equal to C x plus d u. Now, if you look at this one, y, the output is V naught. Now, V naught represented in the state space form. Now, V c is our state variable which is multiplied by 1. So, c is nothing but 1 in this case, and u is V g, and V naught has no direct dependency on V g, it is only through R and C's. So, there is no feed forward term. So, this becomes 0. So, this is your output equation. So, if you look at these two terms, the two equations, this together with this form the state space representation. Of the RC circuit that we just saw. So, every such system, whether it be circuit or electromechanical system or mechanical system, any physical system for that matter, should be brought into this form for representing the dynamics called the state equation, and it should be brought into this form representing the output, which is the output equation, together called the state space representation. So, this is how one goes about obtaining the state space representation of a circuit, the simple RC circuit that we saw. Any circuit for that matter will follow the same approach followed by same approach as indicated, that is steps 1, 2, 3, 4. First step is to identify the energy storage elements. This will give you a direct measure of the number of integrators, and therefore, the order of the system, and therefore, the number of differential equations that are needed, that are necessary to model the system. The second step is to, as we saw in the case of the simple circuit, we identified the variables for the RC circuit, and that is what we need to do here in the as a second step. Identify all the variables in the circuit, identify variables, and I will indicate it as u and x, meaning the input variables and the state variables. So, state variables would definitely be the voltages across the capacitors and the currents through the inductors. So, they directly will be qualifying as state variables, and the input variables, whatever is the input to the system. These variables you need to identify, make a list, and the parameters of the system, and I will call that one as the A matrix. Parameters like the R, C's, the value of the L's, time constants, so on and so forth. Now, this list has to be made, and you can use only variables from this list to make the equations, and that is, you start making the equations starting from dynamic components, make the equations one by one. If there are more than one dynamic component, start with first one, maybe a capacitance, then make the differential equations for that. Next, pick up another dynamic component, probably an L, and then perform the dynamic differential equation for that, and like that get all the differential equation which matches the order of the system. And then put all the equations in the form x dot is equal to a x plus b u, y is equal to c x plus d u. In this form, you need to represent the system, and from there on you can do the controller design. So, for practice, I suggest that you try out many examples, and one of the examples could be a simple R L C circuit. You see, this is a second order system. You have two dynamic elements L and C, therefore, order is 2. You will have two differential equations. Practice on this. Probably you could also have a motor system like a simple DC motor system with mechanical shaft, inertia, bearing friction B, and then develop the relationship, the state equations. Okay. Practice with as many equations and circuits as possible, and we will continue in the next class from here on. Thank you.